Started by looking at momentum. Somebody who was in class on Tuesday explained the general idea of momentum. The general idea of what momentum is.
It's an object's mass times its velocity.
Good. An object's mass and its velocity. And we actually multiply it. So if a person is really big, but they're running really slow, they don't have a lot of momentum. But if a person is really small, but they're running really fast, they might have a lot of momentum. And we talked about the examples with like football. Some football players are tiny and they can tackle these big football players. One, because they hit harder, but they hit harder because they have a higher velocity. Okay? Hit harder. So like imagine a small person tackling a big person. Ever see a lineman pick up a fumble? Okay, in the middle of a football game, there's a fumble. Sometimes a lineman will pick up the fumble, and you see them running, and they run a little bit slower than the running backs. You'll see a running back catch up and tackle it. How are they able to tackle it? Because they have so much velocity. So, a train is very, very massive, but it might move very slow. Have you ever seen a freight train move?
Yeah.
They carry like coal, they move really slow. Now, a car going really fast, might have the same amount of momentum as a train because it's going really fast. So the idea that we talked about on Tuesday is that if you have a high velocity, you can have a high momentum possibly. If you have a high mass, you could also have a high momentum. We have to consider both things. If you are not moving, do you have any momentum?
No.
No, and that's logic. I am not moving right now. I have no momentum. The minute I start moving, I have some momentum to me. Okay? Now, the first thing I'm going to do is go for an example. Yeah.
What type of movement are you referring to? You can be standing still and moving your arms.
Yeah, again, guys, I'm talking about general movement right now. We're going to talk about linear momentum. There's also something called rotational momentum. We're going to talk about linear. Here's a very easy example, and I did it earlier and it didn't work too well. I think it'll work pretty well. Imagine, if you will, you have a basketball and a tennis ball. Now, if we think about Newton's laws tell us that all things fall at the same rate. So remember how g is negative 9.81? No matter what object you are, it should fall at the same rate. So if I were to let them go, they should hit the ground at the same time. So if I drop them in tandem or at the same time like this, if I drop them, they're going to fall like this the whole way down. When this ball hits the ground, what do you suspect might happen? They'll bounce up, right? Okay, they'll bounce up. So if I drop them together, watch what happens now. The tennis ball shoots off, but the basketball doesn't shoot off. Now, think about it this way. This has a lot of mass, right? This has a very little bit of mass. They are moving together at the same velocity. They're moving together. Now, all of the momentum from this one, imagine this mass is 10, and this mass is 1, okay? This has 10 times as much momentum as this one does. It hits the ground, then the basketball shoots up and transfers its momentum into the tennis ball. And it transfers it and it shoots it off at a high velocity. So if you think about it this way, all of the momentum in the ball goes into the tennis ball. Some of it comes up a little bit, so some of it stays with it, but most of it transfers. So why is this such a high velocity? Because it transfers, good, and why else? It's smaller, it's got less mass. It would be like me saying this to you. Imagine you had a hockey puck and a hockey stick, and you hit the hockey puck, right? Then you have a hockey stick and a garbage can, and you try to hit a garbage can. Is it going to go anywhere? It might move like what, foot or something? Okay, that's logical. Not forget meant for each other or not. Think about it logically though. Okay? You hit something like a hockey puck or a baseball with a hockey stick, it doesn't matter anything. If it has more mass, it's harder to move. It's harder for me to move this desk than it is for me to move this ball. Okay? So think about momentum as the mass of an object and the velocity of an object. Those are the two things you want to be thinking. Now, when we go into our examples, we're going to talk about how they're related. So we start with our definition of momentum. Momentum is represented by a lowercase p. A lowercase p, not a capital P. Okay? Lowercase p equals mv. Momentum, a capital is power, yes. Momentum equals mass times velocity. That's going to be our general definition that we're going to continue to use. Now, last chapter we talked about something called conservation. Remember when we had conservation of energy? What did we say based on conservation of energy?
It can't be created or destroyed.
Good. It can't be created or destroyed. The energy in the beginning equals the energy at the end. Same thing applies for momentum. Same thing applies. We can say momentum in the beginning equals momentum at the end. See, sir?
How are you going to know if it's lowercase p if you give us like a blank piece of paper?
Because a capital P would look like this. Taste here. Look at the equal sign. Look at the equal sign. If the P the circle part of the P is lined up with the equal sign, it's momentum. If you see P equals mv, you have to know that it's momentum. If you see P equals W over T, that's power, because that's the definition. So this is stuff that you need to memorize, okay? If it's on paper, if it's typed up, you can clearly see whether it's capital or lowercase, okay? Teresa, same question? No? Okay. All right, so what I want to go through are a few examples here today. I want to look and think for a second. Before we go into the math behind it, we're going to do some conceptual stuff. So, how does, or who can explain, using momentum terminology, using momentum, how does a rocket ship work? How does a rocket ship work? Using momentum.
I don't know. I have an idea.
Good. The rocket ship applies a force. How does it apply force? Think about a rocket ship taking off. What's launching it up to the air? The fire boosters below it, right? So, it's got these boosters at the bottom. It's got boosters at the bottom, which shoot like fire out of it. And suddenly it starts moving up. It's because this. It's first of all, it's Newton's laws. Equal and opposite reaction. You apply force down, it's going to move up. But think about momentum. It has some sort of momentum that is shooting out. Well, momentum before equals momentum after. So the momentums have to be balanced also. So if we think about an example, this is not going to work too well. Let's see if we have, okay. If we have any object that can roll, so let's say we look at this chair. If we have an object that can roll, if I were sitting in this chair and somebody was over there and I wanted to pass them the ball, if I throw this ball hard enough, I will start to do what? Move back. Okay? Again, equal and opposite reactions from these laws. It's also the same thing as momentum. The momentum that I put into this ball, so the ball's mass, let's say the ball's mass is 2 kilograms, and I throw it at a velocity of 10 meters per second. Then I'm putting a momentum of 20 into the ball. Again, 10 kilograms, 2 meters per second. 10 kilograms, 2 meters per second. So the momentum of the ball is 20. Now, if the momentum of the ball is 20, and I know my mass, I can figure out at what velocity will I go back. Okay, by setting them equal. I can say that the momentum I put into the ball is the same as the momentum that will push me backward. It's not going to work that well because the floor has a lot of friction. But if I really throw this, I barely move. Okay? If you do that, if you do it on ice, if you're on ice, ever go ice skating before, and you're standing next to somebody, if they push you, don't they actually slide a little bit too? It's the same idea. If two skaters are standing together and they both push off, they'll both go backwards because their momentums are pushing. Now, if they have different masses, one might go this far and the other one might go this far. So imagine like an older gentleman and then a little kid. If you push the little kid, that kid's going to fly, right? And you're only going to go back like a little bit. The kid has a little bit of mass, he's going to go a lot further. There's a lot more velocity. Okay? So if you think about momentum, it's a balance between mass and velocity.
So how does ice hockey work when they're fighting on the ice?
Is that how people work when they're fighting on ice?
Yeah, like, I mean, like...
Ever seen like slip and stuff?
No, like when you actually watch like hockey games, they fight, they don't look like they're moving much.
Okay, we're talking realistically now. Okay, imagine if I'm standing like this with ice skates and I push off, I slide back. The minute I turn my skate, what am I doing?
Yeah, you stop.
I'm stopping. So that's why they're not moving. Because now it's a friction surface. That's why they didn't work well. Because there's friction. We're talking idealistically, if there's no friction. If there's no friction, I'm standing straight on my skates, I will slide back. The minute I turn, I'm providing a stopping force or a frictional force. It's like when you stop and you ice skate. You turn, you put your skate sideways, so you provide the friction. So that's why they're not moving, because they know how to work with that. But imagine two people that weren't hockey players, and they were standing straight on each other, and they push, they will separate from one another. Okay? So again, the idea of momentum is a balance between your mass and your velocity. Now, if we look at these problems today, we're going to try and figure out mathematically how we can solve for stuff. And it's the same example of something like a grenade. Think about in a war, somebody throws a grenade. What's happening? There's a lot of energy built up, right, in the grenade. It explodes. And what happens to all the shrapnel? It goes off in every direction. It might hit the soldier or whatever it is, right? So, imagine shrapnel going off in every direction. The mass and velocity are all balancing off of each other. Because think about the object. If somebody takes a grenade, pulls the pin, puts it down, is it moving?
No.
It's got no momentum, right? It's got no flat surface. It's got no momentum. Now, it explodes. Suddenly it's moving. How could you get momentum out of no momentum?
Force transfer.
Force, explosion, reaction.
Vibration.
Okay.
Wait, what was the question?
You have a grenade.
Potential spring in
You
there.
have a grenade with a
Yeah,
little,
that's
what's that called? Clip? Is it called a clip? I don't know. Anyway, the little thing on the pin. Pull the pin. The grenade is here. It's sitting still. You pull the pin. What happens to the grenade?
The stuff inside falls to the bottom.
It explodes, right? It goes off in every direction. All the shrapnel goes off in every direction. There was no momentum here. So really there can't be momentum here. What's happening is this. All of these are balancing each other out to give a net zero. So for example, this piece of shrapnel might have momentum of negative 20 left. This one would then have a momentum of positive 20 to the right. This one might have a momentum at an angle of 20 degrees of negative 20. This will have a momentum at 20 degrees at positive 20. So even though it looks like there's momentum, the momentum of the whole system is still zero. Again, it started with no momentum because it's not moving. Even though these are all moving, they have each piece of shrapnel has its own momentum. But each piece balances out the momentum of the other. This has a negative momentum. This has a positive momentum. They balance. This has a negative in both directions, a negative in the x and a positive in the y. This piece of shrapnel balances that momentum out. So they end up balancing each other out. So if you did like sum of all the momentums, you're still going to get zero. So the idea of conservation momentum does exist. And it is true, even if you have zero before and something explodes, it still is zero after, because they're all balancing each other out. Okay? So for momentum, it is important to know what direction you're traveling in. Remember for energy, it really didn't matter? Remember for energy called non-conservative forces? It could have gone like this, it could have gone directly down, but the change in energy is the same for both those situations. Here, it doesn't work that way. Momentum, the sign matters. So if you're traveling left, your velocity is negative in the x. If you're traveling right, your velocity is positive in the x. If you're traveling up, your velocity is positive in the y. If you're traveling down, your velocity is negative in the y. Okay.
I was wondering, what do you mean by how they balance each other out and how like momentum equals zero? Like, because I mean, after even though they start at zero with no momentum, in the end, like after they blow, like when they explode, the pieces are still moving.
Yeah, but it's the
Pieces are still moving. Yes, but they're balancing each other. The momentum of this piece of shrapnel is positive to the x. This one is negative to the x. They're balancing each other out. So if you sum all the momentums of all these pieces, you'll get zero.
Oh,
Because it started with zero. But individually, they each have momentum of their own, yes.
Yeah.
But the system is still zero.
Okay.
Okay? That's when you talk about a system and its parts. Terrence.
Now, what do the delays come in at? Like grenades, like that?
The delay is just so you can get cleared from it. And it's just a little thing inside of it that delays it. That's all it is. So like when you pull the pin in there, if you hold it down still, it won't go off. You can hold it down with your hand. That's why I ever see like these movies with like, I don't know, they're in war and like somebody will like pop a pin and put it in the person's mouth. It won't go off until they actually open their mouth. So it's like they're pretty much torturing somebody. Like you have to keep your mouth shut or else the grenade is going to go off in your mouth. So the idea of that is like the pin is held down. Now, once you let go of it, it's not going to go off right away. There's a little timer in it. Once you let go, then the timer in the system starts, it's a little gear. And it starts to crank and eventually it'll go run out. So there's a delay. But the delay is not the momentum.
Once you get out. Once you get out.
That's exactly, I was going to do that next. Shotgun. Alright, next example.
We go down G style. One bullet, hit 6 chest.
Next example, guys. If people learn how to fire guns, okay? If somebody learns how to fire a gun, you have to think about the fact that it has what's called backfire. Okay, so recoil. If you fire something that's small like a pistol, there's not much recoil on it. If somebody goes hunting and they have a shotgun or a rifle, you have to tuck it underneath your shoulder, or else you can break your collarbone. If you hold, imagine this was a rifle, I know it's not, and you hold it up to your shoulder and shoot, you can break your collarbone. So they teach you to shoot a certain way. You can tuck it under your arm usually, so the recoil won't hurt you.
How do you know?
If you think about it, it's momentum. Now, the bullet has a very small or large mass. Small mass. But what does it have a lot of? Momentum because of its velocity. So, if we think about the example of a gun with a bullet, the gun is here, the bullet is coming out of the gun the bullet has a very small mass. Say the mass is 1. Okay? It's a box, I know. Say the mass is 1. And we'll say that the velocity of the bullet coming out of the gun is 200 meters per second. It's always very high velocity, in 1 kilogram. Okay, now, the question becomes this. If we want to figure out the recoil on the gun, we have to know how massive is the gun. Okay? So let's say the mass of the gun is, let's say, 10 kilograms. 10 kilograms, actually that's not true. 10 kilograms is 20 pounds. Let's say it's,
Guns can have it.
they could be heavy, shotguns could. Let's say 8 kilograms. That's a rifle, it's not a pistol. Okay, a pistol might weigh a pound or 2, but a rifle might weigh like 10 pounds. An egg. That's what we're going to get to in a second. Hold on 1 second. Now, the question becomes this. If we want to figure out the recoil, we need to know what the velocity of the gun will be. Now, we know that the momentums have to balance each other. So the momentum of the bullet is 200 times 1, right? The momentum of the gun has to be something out balancing it. To balance it, it must be negative. And think about it logically. If somebody fires like a paintball gun, the paintball shoots forward, the gun goes backward. The velocity of the paintball is positive, the velocity of the gun will push backward, thus negative. So your answer here, okay, we want to say that the M of this one and the V of this one must be the same as the M and the V of this one. Okay, and before you shot the gun, you're standing still. Do you have any momentum?
No.
So together, these two have to be 0. Again, this is the momentum of the gun after, this is the momentum of the bullet after. We can say gun, we can say V for bullet. So afterward, the gun and the momentum of the gun and the bullet is equal to 0. Because remember, the momentum in the beginning is the same as the momentum at the end. This is the momentum in the beginning, 0. This is the momentum at the end, the combination. So since the bullet is going to be a positive value, this must be, by default, a negative value. Because negative and a positive is what gives you 0. So here, for this problem, let's plug in our numbers here. Somebody had a hand in the back.
We all have hats.
Somebody raised a hand in the back.
I did, basically.
Good? So for the bullet, we have the mass is 1 kg, which is not the mass of a bullet at all. The mass of a bullet is like 0.005. I'm just using 1 for simplicity of numbers. Okay? 1 kilogram, guys, is 2.5 pounds. A bullet is not 2.5 pounds. Okay? Times 200 meters per second.
Definitely choked.
8 kg, thank you, Star, very good. And VF. Now, use your logic. What number does this turn out to be? 200. 8 times what number is 200? 25. So this is going to be negative 25 here. You could also just solve for VF. You can move this over as 200 and then divide by 8. So if I were to do that, I would get 8 VF equals negative 200. Again, I'm subtracting 200. Subtract 200 from both sides. And I'll get divide by 8, divide by 8. And again, VF, as Star just said, will be negative 25. What would my units be? Velocity? Meters per second. Now, the thing about momentum is there are no new units. So momentum, the units are whatever you get. It's mass and velocity. So kg, m over s. That's the units of momentum. Let's go through that. Remember at the beginning, we defined momentum as mv. M's units are kilograms. The units of velocity are meters per second. We always use kgs. Remember, we don't use grams because most things are on the kilogram level. Okay? So the units for momentum are kg m over s. Okay? So if you want to write it as 1 unit, that's the units for momentum. Okay? But clearly, our answer was in meters per second because we solved for velocity. Remember, kg times m over s. That's your units for momentum.
That was what we talking about, like
No.
grenades.
Excuse me.
Oh, that make the bullet explode.
Yeah.
Yes, like a
That's what
shotgun.
the guy was talking about this when I was there.
Oh.
The Secret Service guy was talking about
There's a Secret Service guy here?
They had a business.
Really?
Yeah.
I gotta get a good listener now. That's not fair. Secret Service. Alright, sorry.
And you shoot a gun, it makes there's more damage. Back then it can go in from out.
It's just like it.
And that's why a shotgun is so deadly. Shotgun shoots like 7 shells.
That's what I was thinking of grenades.
That's right. Star's example is great, guys. Think about guns that the bullet explodes. There are guns where when you shoot it, either it shoots different parts of the bullet, or the bullet itself explodes like a shotgun. So if you, they're not legal, obviously. Yes. The bullet exits the gun with a velocity, and then the bullet itself explodes. So that would be like a momentum problem and another momentum problem. The momentum problem we just solved is the bullet in the gun. Then the bullet exploding is a whole other momentum problem. It's like the grenade. Okay? The momentum problem for a bullet exploding is exactly like a grenade. Alright.
What about that's what with rapid fire?
With rapid fire?
Yeah.
What's the question? What about
rapid? Like, would they all come out at the same speed, or would they all be different?
No, they're the same speed. There's just a time delay, whether you notice or not. Like no automatic, like a machine gun, pretty much. You're saying?
No, like I don't know.
What else is rapid fire besides a machine gun?
I don't know how to explain it to you.
There's guns that are non-automatic, then there's semi-automatic, then there's automatic.
I don't know so much about guns.
You play video games? Come on.
It's kind of like a Modern Warfare where like you see that you can add like rapid fire, it's like 5 different bullets that come out.
That's not rapid fire. That's like multiple fire.
Yeah, that's
Rapid fire is a machine gun where it comes one after the other. You're talking about like simultaneously shooting 5 bullets.
yeah.
It's the same problem, except now you have 5 bullets coming out. Momentum of 5 bullets counteracts the momentum of the gun. Guys, I don't even know about Johnson's video game, so. Malcolm. Yeah.
Thank you.
You're welcome.
Wow.
Alright, let's use logic next. If we got 2 cars going, so 2 cars are traveling.
Hold on, let me write it.
Just think, you don't have to write, just think. If 2 cars are traveling, if car A is 3 times as big as car B, what has to happen for them to collide and stop? What does this car have? Okay, let's go through this though. This car is 3 times as big as this car. So this velocity must be, what is it? 3 times higher, but 3 times. Again, if this car's mass is triple this car's mass, for them to have the same momentum, this has to have triple velocity. Okay, it's a linear relationship. Again, if this is triple the mass, and you want to have the same velocity, the same momentum, this has to have triple the velocity. So imagine a truck and a car. A truck might have 3 times the mass of a car, but the car is going 60 and the truck is going 20, they will hit and actually stop. They'll have counteracting momentum, so they'll stop. Okay? Again, the idea of momentum is very standard or very, it's not square. You don't have to worry about like energy, where we squared the b and went out by the square of it. They are directly related to each other. Okay? Alright, let's look at an example with math.
Bill Nye.
Yeah, well, let's open up.
Yeah, you can. You make it a lady, so they don't have a lot of ladies.
A lady visitor to talk about physics?
Yeah.
Why would it be a lady visitor?
What?
Something nation.
Why did it be a lady visitor?
I'll try and find one. Don't say
Wait,
it.
why did it be a
Did you hear what he said?
Why did it be a lady visitor?
Karen, Karen, Mom.
He said that they don't exist. Exactly what we need to find.
Okay, fine. It's such a small number.
Sure, they are smaller, but they do exist.
So we don't count the men as certain women.
All right. If you say the comment, my comment does not look bad.
That was the point. You're like, find my wallet.
Alright,
You can just come back with
so here's what I want you to think about. Imagine please, if you have, you know how a train is made up of many cars? Or several cars and they're all linked together? Okay, imagine you have a car here, you have a train car here. Now, this car is at rest, the other car is moving. The other car is going to run right into it, click together, and then they're going to move together. Okay? So again, this one is going to move to the right, it's going to hit the front car, they're going to click together, their gears are going to lock right here. Okay, they're gonna lock together. Once they lock together, they're gonna move in tandem. They're gonna move together. So again, trains are connected by this little pin here. Okay, the pin will lock in and they'll move together. So a 10 kilogram railroad car traveling at a speed of 24 meters per second, traveling at 24 meters per second, which is a reasonable number, strikes another car that is identical. So it has the same what? Mass, thank you. It's at rest, no momentum, sorry.
Oh, yeah.
Okay. It hits another car, strikes another car that is identical. What will happen afterward if they stick together? Meaning they lock in. Okay? What will happen to the system? And we want to know in terms of mathematical. So what is the velocity? So what is the velocity
0. Oh, I'm sorry. I'm talking about the one at rest.
No.
of them together after the collision? What happens to them, guys? Again, what happens to them? What is their velocity afterward? Okay? We know what the mass will be. The mass will just be double because there are two of them together. So that part's easy. So we start this problem with our conservation of momentum. Momentum before equals momentum after. So please write this.
Does the momentum before, like, does it mean, like, when the car, like, when the railroad car was, like, at its beginning?
It doesn't matter for this problem because it's a constant velocity. It doesn't change. But yes, what really matters, Kenny, is right before the collision. Okay? So, momentum right before the collision, momentum after the collision. Okay? I and F, initial and final. Now, if we continue this down, we know that momentum is defined as mv. So, we have, let's call this car A, and let's call this car B.
Is it going to be like when we had EI and...
It's exactly, yep, same thing. Different equations, but same idea. So, beforehand, there's a mass of car A.
10,000.
There's a mass of car A, initial velocity of car A. We have mass of car B times initial velocity of car B.
Isn't the mass of car?
We know afterward we have mass of car A plus mass of car B because they stuck together. And if they're moving together, afterward, they have to be at the same velocity. So we can just call this VF. Again, take a look at what I wrote here. Let's go through this. In the beginning, they're separate. So you have the mass of car A and its velocity giving the momentum of car A in the beginning. Then you have the momentum of car B in the beginning. We'll know that this is going to be 0 because it's at rest, even though we're writing it now. I want to still write it, show that it's 0. Afterward, they stuck together. If I'm running and somebody throws a football and I catch it, now the momentum of us together is the mass combined, me and the football. The mass combined right here, times the velocity. Well, remember, you're moving together now. If you catch something and you're running with it, the velocity of the ball is the same as the velocity of you. You're exactly the same velocity. So these train cars clicked in, and now they're moving like this. Okay? So we don't have to write VB or VA here, because they're moving together. So I'm just going to call this the final velocity. You could write like A or B, or you could write the velocity of A and B, but I don't ever write that, and you're not going to see that. But if you want to write your notes, this is the velocity of A and B together. Okay? This is the velocity of A and B together.
It's assumed.
Should it be what? Well, how do we know? Because what's going to happen? Make it simpler. You're doing too much work. In the beginning, there's mass. In the end, there's more mass. So what has to happen? If mass goes up, he has to go down. So it will be less, yes. But let's prove that in a second.
Gosh, Christian.
All right, here. MAVA. M is, what is our mass?
10,000.
But isn't...
Times the velocity.
20.
Now, notice, I didn't put negative. It's positive because it's going to the right. If this object were moving left, the velocity would have to be negative. Your signs mean so much with this, okay? If you don't have your signs, the problems aren't going to work correctly. Now, afterward, they're moving together. So what is their mass? 20,000.
Wait, didn't you just miss, like... Oh, yeah.
I ignored it, Kenny. Why?
I know.
because it's at rest. Again, the second car in the beginning was not moving, so we don't have to include it in the equation. It's 0. Now take a look and just simply divide by 20,000. So here's what I want you to notice. Do me a favor though, watch what happens here. Divide by 20,000 on both sides. Don't get a number though, don't get a number yet. I know a lot of you know the answer. When I divide by 20,000 kg on both sides, you're left with df, aren't you? Now, what is 10,000 over 20,000 as a fraction? 1/2. So your velocity is going to be half.
At 0.5.
Multiply these and divide. These cancel to give you 1/2. What's a half of 24? 12.
And you're in calculus.
Alright?
Okay? You got the highest grade in the midterm, so that makes you
Yeah.
think about what you said.
Hey, I want you guys. I want them to think that much.
Giving you a hard time.
Double, you're great.
Now,
I wouldn't even get
in this problem, it only turned out to be half the velocity because it was the identical mass. That's the key here. Because of identical mass. If the mass of the second train car was not 10,000, this number would not be 20,000. If the second car was like 5,000, it would be 10,000 plus 5,000, this would be 15,000. And you would not get the same answer. Again, it's only half because they are identical. Because they are identical. Okay? That's the key here. Is everybody okay with this problem so far?
Yeah.
Just so you know, this is like an easy level problem for momentum. We're going to get a little harder soon. So at rest has no effect on momentum. No effect on momentum when something is at rest. Its momentum is 0. Because it's velocity.
Can we assume that the velocity always has the same mass, even though
If it's at, no, if it's moving, it's different. It's moving.
it's direct?
That is worse. All right, next problem.
What is that
Now.
supposed to be?
Same example, 2 train cars. 2 train cars. One of them is moving to the right with a velocity of 20 meters per second. Its mass is 5,000 kg. Okay? The other one is also moving to the right, but at a lower velocity. So this one will catch up to it.
15. 10. 15. Yeah, 15.
Cool?
Should have made it like 14.9.
That'd be bad.
They are still the same car, identical. Now, we have to think about momentum before, momentum after. So, whoops, hold on, I'm not there yet. Thank you, sorry. All right. Before they collide, they each have their own mass and their own velocity that is separate. Then this one's going to catch up. Clearly it's going to catch up because its velocity is greater. They'll link together and then they'll stay together. So same idea as the last problem, but this guy is no longer at rest. So you know what? It's the same equation. But instead of going to 0, remember the last example? Where this went to 0 down here? It's not going to happen anymore. So now, if we continue this, we got M-A V-I-A plus M-B V-I-B equals. Again, momentum of the first car initially, momentum of the second car initially, they are then stuck together afterward, and they have the same velocity
Did you
afterwards.
label the trains between the
Okay? Same setup as last time. It doesn't matter actually. It does matter. It does matter. Same one as last time, Elizabeth. All right, here we got 5,000 times 20 plus 5,000. Again, guys, you can solve analytically. I'm plugging in numbers for now. Times 15 equals
10,000.
times VF.
You
Again,
divide by 10,000.
both of the cars have a mass of 5,000. One is moving at 20, one is moving at 15. They collide and they stick together. So in the final, the masses are combined. So we have MA plus MB. Then after that, we know that there's going to be a VF together. We want to find that VF together. 5,000 times 20 is 100,000. 5,000 times 15 is 75,000. Okay, again, we don't have to worry about units because I gave everything in SI units here.
Let's do this all
You were
one
given in
time.
meters per second and kilograms. Now,
Let's do it all one time.
175,000 divided by 10,000. What do you get?
A number.
17.5. Take a look at the velocities in the beginning, everybody.
Is
What's the
it
average of these two numbers? 17.5.
That's only when the mass is the same.
Yes. So let's go through that.
Right?
Here, dividing by 10,000 on both sides.
Cars, Disney cars.
Divide by 10,000. You're going to get 17.5 meters per second as the combined velocity afterward. Again, one car was moving at 20, one was moving at 15. The average of 20 and 15 is 17.5. This only worked because the cars were identical. It only turned out to be the exact number. Again, 17.5 is halfway in between 20 and 15. And it only worked that way because the cars were identical. Everybody okay with this so far? Let's keep going. Now again, for those people that want to keep solving analytically, if you solve for VF, you would just have this whole equation divided by this quantity. So if you want to solve for VF in the beginning before you plug in any numbers, just divide by MA plus MB. So put MA plus MB in the denominator. But be careful, you can't cancel stuff there.
Let's add acceleration. You should have acceleration.
Momentum doesn't really involve acceleration. It's always about the quantity of velocity. If velocity is a function that changes, so if the velocity changes, you have acceleration. But if the velocity is changing, then the momentum is constantly changing. You can't figure that out. You'll use an integral, which is the second thing we're going to learn in calculus. You can do with that. Okay, there is a way to do it, but we're not going to do it right now.
Is it like what we're doing in class, like a little bit? No, it could be like.
It's like the area under that curve we did that
Yeah.
one time. Yep, that's what it's like.
Yes, I know. That's not what I meant.
10,000.
Could you try?
Okay, so now we're looking at two different cars here.
Two times.
Figure it out.
Oh, he gave me that look. He gave me that wink and the look. It's like, so you're on the right track. Take it back.
Oh, man.
This formula would you give?
Same problem, guys. Same problem. Car A catches up to car B.
Immediately.
They link together. We want to find the velocity of them together afterward. Same formula, same problem.
No, I wrote down the most.
They're both positive. They're both positive velocities. So both to the right.
We have one stop.
Why are you adding them?
No, I mean I know, but still, like, so you were both like, starting with the initial, like one stop. Yes, but then like one.
What's your favorite class?
Huh?
What's your favorite class?
Better than
It was my favorite class in high school.
It's better than English.
Yeah.
I'm not sure you hear it. Reading.
Y'all can just talk and all
It was by far my favorite class in high school.
English is my
I liked English too. I loved reading it. I really did. Not until 11th grade though. I never read a book until 11th grade.
You never read a book until 11th grade?
Like a full novel until 11th grade.
Yeah, I always read like policy.
I would get like 10 pages in. I never read books when I was a kid.
It's like,
I love books now. I read them all the time, but I don't know what it was when I was younger. I just didn't like.
At the same time,
That's why you make them words.
Hey,
Yes,
let me
exactly.
tell
He
you.
makes it like 12 syllable words just to make himself feel better.
Remember, that's a plus there. Sorry. Okay. Now, for this problem, I'm going to solve this one analytically. Okay? You can solve it the same way. Plug in your numbers and divide. I'm going to just solve analytically though.
See what happened?
Yeah.
You just divided by MA.
So again, all I'm doing here, remember earlier, we got a number like 10,000 here, and then we divide it?
I think I get this. I thought something else was just on It just disappeared.
So I looked up.
Yeah, it is.
Looked up, it was gone.
What?
I was writing the 20 minutes.
Ah, okay.
And I just seen that.
I scrolled down. So again, this was a number here like 10,000 before, and we divided by 10,000 at the end. I'm doing the same thing. Please, please, don't cancel m's. They can't. This is a binomial. There are two terms. You cannot cancel the m's. Many students forget that. They start canceling m's, and then what happens? You're left with just v's. Doesn't make sense. Okay? If you cancel all the m's, you're left with v plus v. And that just doesn't make any sense. You're just going to add the numbers together. Now, solve this one. Nice guy.
What confidence does to you? Makes you crazy.
Solve, please.
Something thousand.
The sum of the masses, what were the masses again?
10,000 and 5,000.
All right, so 15,000 together is their masses.
Yes.
This number was 20 and 12. So,
Is there a way to put like zeros on the calculator? Like type in zeros.
So about 10, like 10 to something.
Yeah, you can try to.
10 times.
One.
Is it 200?
The 3 indicates how many zeros there are. Scientific notation.
Yeah.
What do you get? What did you guys say? 17.3? All right, it's extremely important that we discuss this answer here. Let's go through this and think for a second. Think logically. Which train car, looking back at the beginning, this train car has more mass, right?
Yeah.
And its velocity is 20. If I just average the velocities, what would I get? What's halfway between this? 16, right?
16.
It would, if you just average these, it would be 16. So if these were the same mass, the velocity would be 16, like in the last problem, the average. We got 17.5. Now though, take a look. Our answer was 17.3, which is closer to this than it is to this. Again, the average of these numbers is 16. Our answer was 17.3. Isn't that closer to 20 than it is to 12? Why is it closer to 20? Because why? Larger mass. Again, this has a larger mass, so its velocity weighs more. Not weigh as in waste, but weighs more as in has more effect. The thing with the higher mass, its velocity will be more of a weighted factor in a sense.
Hold on.
Please don't write word for word. You gotta rewrite your own words. Come on, I've said this. The object with a higher mass here has more of an effect on the problem. So since its velocity was 20 and its velocity was 12, the actual velocity will be closer to the one with the higher mass here.
Give it to me in like in a situation why? Like why? Like in a situation, why exactly does, not just because the math, I'm not talking about just the equation, just like an example. I don't care about the logic, I'm not for an example. It does the logic, leave me alone.
At the same time,
Okay, yeah.
I can't write it down.
But that's what I
I can't get journalists. I'm falling asleep.
Look at the momentum before. This momentum is much higher than this momentum, right? So when you're trying to find the momentum together, it's going to be closer to the one that had more of an impact. When they collide, right, which has more of an impact? The heavy one, right? So the overall velocity will be closer to that one. So this one slows down, really, and this one does what? Speeds up.
So what about the whole math of that?
Stars.
I don't think I can solve the math.
Stars all up there. Yeah, it's all up there.
If you change the number to 30, that number changes because more than that. The velocity does have an effect. But the mass right now.
Real laugh.
All right, next thing. Notice. Notice. Come on. You shouldn't have to say the word notice 3 times. Notice here, this car started at a speed of 20, or a velocity of 20 meters per second. This car started at 12. So, when they collided, what happened to this car? It what? It what? It lost velocity, or it got slower. So, this car got slower. This car, what happened to it? It sped up. So it's like, yes, it's like something going slowly and something going fast. When it hits it, it speeds it up a little bit, but it slows this car down. It's the same thing as if a car was driving, guys. It's just like an accident. Oh, when it starts to like slide off the road? Drag is friction. Drag could be air resistance. Drag could be
So
more on the floor. When it hits and they start to glide together, it's just the term for a car when it slides is drifting. Maybe Tokyo Drift, the movie, or Fast and the Furious. All right, next problem. What about it? It's like energy. Yeah, same idea. Momentum is moved from one to the other. Yes. For tonight, here's what I want you to do. Last night you were supposed to read 188 and 189.
I did.
It should have taken you about 3 minutes to read, guys. Or, sorry, 198 and 199.
You just know what?
Last night you were. Tonight I want you to read. Tonight I want you to read from page 205.
What?
Page 205.
To 300.
You read it for me.
205 to 208. And 208 is an example, so you're going to read an example. Do not overlook the example. So tonight, you're reading 3 pages, 205, 206, 207, and then on 208, you're going to look at that example. After you've done that, what I want you to practice is one problem.
205 to 208.
205 to 208 reading.
Anyone have a problem?
I'll tell you the problem on it.
I did so much stuff on one day, man.
Try page. Page 214, number...
I didn't even know.
Try 1 and 2.
New York City.
2 problems, guys. Numbers 1 and 2, please.
Yeah, we did.
The library's open. Sure, make it count. You get your turn on 7 or? You can do it right now if you want. Let me stop recording actually, so we don't.